A repair drone floats inside an orbital assembly bay. Above it, a damaged telescope module flashes an amber docking signal. The drone can see the destination, but seeing the destination does not mean its controls can reach it. The flight computer currently offers only two programmed maneuver pulses, B1 and B2. Both lie along the station's maintenance deck. The target sits above that deck. When the computer asks for an upward maneuver, every available recipe slides sideways instead. The problem is not distance, it is freedom. Each maneuver pulse is a vector in command space. Its direction tells how the drone's velocity will change, and its length tells the strength of the pulse. Paired thrusters let a coefficient be positive, negative, or zero. So the computer can apply twice B1, subtract part of B2, or combine them. A typical command has the form delta V equals AB1 plus BB2. The numbers A and B are not new directions. They are instructions for how much of each available direction to use. This is a linear combination. Now stop watching one result and ask for the complete collection. Include every command that can be built from the available pulses. That collection is a linear vector space. It must be closed under the operations we are using. Add two valid commands and the result must still be valid. Multiply a valid command by any allowed scalar, and it must remain in the space. Choosing a scalar of 0 gives the 0 vector. No velocity change at all. Reversing a command gives its negative. The origin is therefore not optional. It is the command that does nothing, and every vector space must contain it. These rules turn a few control directions into a complete mathematical world. What does one available direction create? Scale B1 by every real number. Its endpoint can move forward, backward, or return to 0, but it never leaves one straight line through the origin. We say that B1 spans that line. Its span is the set of every scalar multiple of B1, and the line has dimension 1. Bring back B2. It is not a multiple of B1, so it opens a genuinely new direction. Vary both coefficients, and the possible endpoints sweep across an entire plane. Every point on that plane is one linear combination of B1 and B2, and every such combination stays on the plane. This is the span of B1 and B2. The computer now has two independent degrees of freedom, so this reachable space has dimension 2. The orbital bay itself provides a larger three-dimensional command space, V. Our bright maneuver plane, W, lives completely inside it. Because W contains 0 and remains closed under addition and scalar multiplication, W is a vector space in its own right. It is also part of V. We call W a subspace of V. A line through the origin inside W is an even smaller subspace. The nesting is real. Line inside plane, plane inside volume. The phrase, through the origin, matters. Copy the same plane and lift it upward. The shifted sheet still looks flat. It is a perfectly good geometric plane, but it is not a vector subspace. 0 is missing. Add two commands whose endpoints lie on that shifted sheet, and their sum generally lands on a different sheet. Closure fails. A subset of a vector space is not automatically a subspace. Now the engineers add a third programmed maneuver, be redundant. It enters dramatically, but the reachable plane does not grow. The new command is just B1 plus B2. It offers another recipe for motions that were already possible. 3 arrows are visible, yet the command space still has only 2 independent directions. Hardware count is not dimension. This redundancy gives us 2 separate questions. Do the commands span the desired space? And are they independent? A spanning set may contain unnecessary directions. An independent set may still be too small to reach everything. A basis succeeds at both jobs. Its vectors are linearly independent, and together they span the entire space. For the maneuver plane, B1 and B2 form a basis. Remove either, and the plane collapses to a line. Keep both and every in-plane command remains possible. Add be redundant, and nothing new becomes reachable. The basis is therefore a minimal complete control vocabulary. The number of vectors in any basis is the dimension. Different valid bases for this plane may point in different directions, but every one of them contains exactly 2 vectors. Dimension belongs to the space, not to our choice of arrows. The repair target is still outside that 2-dimensional subspace. The drone needs a command that cannot be built from B1 and B2. A violet pulse, B3, rises out of the plane. The instant it does, the reachable fabric opens from a sheet into a volume. Now, B1, B2, and B3 are independent, and together they span the full 3-dimensional command space. They form a basis for V, and the dimension of V is 3. At last, the target has a valid command recipe. The computer selects 2 copies of B1, subtracts 1 copy of B2, and adds 1 copy of B3. The component motions assemble into one velocity change. The drone follows that command and reaches the telescope module. What looked like a navigation problem was really a question about span. Was the target command inside the space generated by the available controls? The 3 coefficients can be stored as a coordinate column. Relative to the basis B, delta V has coordinates 2, -1, 1. These numbers are not the physical maneuver by themselves. They are its recipe in the chosen basis. Change the basis, and the recipe will change. Keep the final velocity change vector fixed in space. Around it, replace basis B with a different set of 3 independent directions, basis C. The colored component pieces rearrange, and the coordinate column changes, but the physical vector does not move. One vector can have many coordinate descriptions. A basis is a language. Coordinates are the words used in that language. This distinction will matter later. Changing a vector is an active transformation. Changing the basis while keeping the vector fixed changes only its description. The matrix whose columns are the basis vectors translates coordinate recipes into vectors in the ambient space. Its inverse translates the same vector back into that basis's coordinate recipe. A basis does not need right angles. Our original control directions are oblique, and they still span the full space. But oblique controls share components. A pulse intended along one direction can contain some motion along another. Perpendicular controls separate those contributions cleanly. When different basis vectors have inner product 0, they are orthogonal. When each also has norm 1, they form an orthonormal basis. Right angle markers show orthogonality. Equal unit ticks show normalization. How can the flight computer turn an oblique basis into an orthonormal one without changing the span? Schmidt supplies a geometric recipe. Keep the first direction and normalize it. From the second command, identify the shadow pointing along the first. Subtract that projection. What remains points in a genuinely new perpendicular direction. Normalize the remainder to obtain E2. For a third direction, subtract the parts already explained by E1 and E2, then normalize what remains. Nothing magical was added. Schmidt only reorganized the same space into cleaner independent directions. If a supposed new command were actually dependent, subtracting its old components would leave the 0 vector. That 0 remainder is the algebra announcing that no new dimension was present. So far, our command space has matched the 3 visible directions of the orbital bay. But dimension is not limited to physical space. To predict the drone completely, the computer may store 3 position coordinates and 3 momentum coordinates. One state is then an ordered set of 6 numbers, x, y, z, px, py, pz. The corresponding phase space has dimension 6. We should not draw 6 literal spatial axes. The geometry is an algebraic extension. 6 independent coordinates require 6 basis elements. The same idea scales to hundreds, millions, or infinitely many coordinates. A sound waveform can be expanded in frequency modes. A deformation can be expanded in normal modes. A function can itself behave like a vector. What matters is not whether we can draw the space. What matters is that its elements can be added, scaled, combined, and described relative to a basis. Quantum mechanics uses complex vector spaces. A quantum state can be expanded as a linear combination of basis states, with complex coefficients C1, C2, and so on. Those basis states are not ordinary arrows floating inside the orbital bay. The picture is a schematic for the algebraic structure. Magnitude and phase live in the complex coefficients. In an orthonormal basis, inner products isolate the coefficients cleanly, and normalization requires the sum of their squared magnitudes to equal 1. So the vocabulary survives the leap beyond visible geometry. Span asks which states can be constructed. A subspace is a smaller complete family of states. A basis is an independent spanning set. Dimension counts the number of independent basis elements. The abstract setting is larger. But the logic is the same logic the drone used to reach its target. One final question prepares the next lesson. Let a linear operator T act on the full vector space. The command lattice shears and stretches. Most test directions leave their original lines. Their transformed vectors point somewhere new. But one luminous line behaves differently. Every vector beginning on that line is transformed into another vector on the same line. Its length may change, its direction may reverse, yet it never escapes the line. That line is a one-dimensional invariant subspace. T maps the subspace back into itself. Span told us what could be built. Subspaces revealed complete worlds inside larger ones. A basis removed redundancy. Dimension counted independent freedom. Orthonormal bases made components easy to isolate. Now, an invariant line has survived an operator. Next time, we will identify the non-zero vectors that span such lines and measure the scale factors attached to them. Those vectors are the eigenvectors, and the scale factors are their eigenvalues.